Hello everyone, I am Professor Pankaj Vishwas. This is my first lecture on fundamentals of thermomechanicals and fatigue analysis of welded structures. So, in this lectures I am going to deliver a topics whose name is weld induced thermal history. Here I will discuss the basics of heat flow in welding. So, here basically what are the content of this today's lecture. Here I will discuss the governing equation of thermal analysis, then boundary condition of thermal analysis I will discuss, then what are the different stages generally we have seen or we used to seen that in welding process, that related things I will discuss. Apart from these things I will discuss different types of solution of this governing equation used in welding technology. Here I will discuss if there is a fixed point or line heat source, then what should be the temperature distribution over the entire welded structure, or you can say welded plate, that related things I will discuss. Apart from these things I will discuss also moving point heat source. So, first of all I will discuss about due to point heat source at a fixed location, or you can say fixed heat source in welding, what is the thermal history over a welded plate. So, after that actually I will discuss if the heat source is moving in nature, then what should be the thermal history over the entire plate of that welded joint, that related things also I will discuss. So, generally one things we should know that to determine the weld mechanics, two different fundamental analyses generally are required. What are those fundamental requirement for welding mechanics? The first one you can say is called heat conduction. So, details about heat conduction related things I will discuss in this course. So, what is heat conduction, that you are very well familiar. In case of heat conduction, you can say conduction is the transport of heat energy in a medium due to temperature gradient, and the physical mechanism that can be in random atomics or molecular activity. This is generally you are very well familiar. This is generally called conduction. Then due to this conduction, how the temperature distribution or governing equation of heat conduction is coming, that related things in details in this course I will discuss. Apart from this thing, another very important analysis is required to determine this weld mechanics is thermal, or you can say thermal elastoplastic analysis. Why this is called thermal elastoplastic analysis? Because welding is such a phenomena where generally there is occurred some uneven expansion and contraction types of phenomena due to welding, heating and cooling. Due to these things what happens, there occurs some permanent types of deformation, as well as there is due to contraction there is occurs some recovery of deformation, that you can say. That means some elastic deformation as well as plastic deformation is generally taken place what is called in case of thermal in case of welding phenomena. Due to these things what happens, the another mechanics which is required to understand or analyze the welding process, that is called thermal elastoplastic analysis, that also I will discuss. So, whatever the two different mechanics generally required to understand the what is called welding mechanics, that related thing in this course I will discuss in details. But in today's lecture I will basically consider the concept of heat flow, or you can say fundamental of heat flow in welding, that related things I will discuss. Okay. Now, the most important factors which governing this above two mechanics, you can say is grouped here. You can say the most important or significant factor which affect this mechanics is, first one is the heat input in welding, or you can say heat input rate. What is heat input rate? Heat input rate means you can say heat input, its unit is joule. How this heat input is coming, you are very well familiar in welding. If it is a arc welding process, then you know this heat input generally you can say eta Vi, where eta is equal to arc efficiency or welding efficiency, you can say V is the welding voltage and I is the welding current. that is that things you know very well. What is the unit of these things? This unit is watt. With this if you multiply time, that means rate, then what happens, you can say that generally convert into heat energy. This is a power form, and once it multiply with time, this will convert into what it is called energy form. Okay, that unit will be generally joule. This you should keep it in mind. Then another parameter which is required, that is called generally the moving speed of the heat source, or you can say this is also sometimes called welding speed. This is also another important parameters, Ws I am writing, and another important parameters, thickness of the plate. These are the things generally affect this you can say above to mechanics significantly. Apart from this thing, there are some secondary factors in welding also which affect this to mechanics, that is heat conduction and thermoelastoplastic analysis. What are those factors? Like it also depends on, you can say it also depends on welding process. This is, you can say, secondary factors. Another one is generally you can say welding geometry, and another one you can say welding sequence, welding tack, welding fixtures. These are the different types of how we are clamping the plates or structure. Everything generally affect this what is called above to mechanics significantly. This you should keep it in mind. Now, first of all I will discuss about what is called this first mechanics, that is called heat conduction in welding. All of we are very well familiar about heat conduction. I have already told you what is heat conduction. So, generally here the fundamental behavior of heat conduction is, you can consider as the heat flux, or you can say heat flux of energy. What is heat flux? Heat flux means heat flow per unit area. This you should keep it in mind. Heat flux, its unit is generally watt per meter square in SI unit. This is generally heat flux unit. Okay, this you should keep it in mind. I have already written here, which I have represented here in Q double dot, you can see. So, that means this a flux of you can say heat energy flow from a hot region to cool region is linearly depends on temperature gradient. This is I have represented here in terms of what is called grad T. You can see this is a grad operator. What is grad operator? I have already written here. Grad operator means del by del x, del by del y, and del by del z in case of 3-dimensional case. Now, what is temperature gradient? Temperature gradient means the difference of temperature between 2 points, that is generally called temperature gradient. That is represented as grad T. This you should keep it in mind. So, here generally this relationship is coming from the concept of Fourier heat conduction equation. What is Fourier heat conduction equation? That related things in details I will discuss in subsequent slides. Okay. I will drive this Fourier heat conduction equation in details. Okay. Generally we know Fourier heat conduction equation tells, that means heat flux, or you can say heat flow, heat flux flow in a medium generally is directly proportional to, you can say, temperature difference between 2 point, you can write del T. It is also the heat flux is inversely proportional to 1 by delta x. The delta x means, you can say, what is called distance between 2 point. Let us get that distance is, let us call delta x. And apart from these things, it is also depends on cross sectional area also. This heat is depends on cross section. At here we are considering that heat flow per unit area, that is why it is written like that. So, once you equate these two, what are the things we used to get? We used to get, in case of unidirectional case, heat flux is proportional to del T by del x. This del T by del x in unidirectional case, in one directional case is called generally grad T. In case of 3-dimensional case, generally this grad this heat flux is you can write as it is depends on del y del x, del y del y and del y del z. This grad operator become this which I have written already. So, heat is conducting, once the heat is conducting in a medium, due to this thing what happens, there generally occurs some temperature rise, that you can say. How this temperature rise is taken place, that generally you can represent it by the what it is called the concept of specific heat, or you can say enthalpy. How it is, that things just I am going to discuss in details how it is actually. What is the definition of a specific heat? You know, a specific heat definition is generally you can say its unit is joule per kg Kelvin. What does it mean? That means for 1 kg of a matter to rise 1 degree Kelvin temperature, how much heat is required, joule, how much joule heat is required, that is generally called a specific heat of that material. This you should keep it in mind. So, due to this heat conduction, whatever the energy is flowing over the medium, due to this what happens, there occurs some rise of temperature. This rise of temperature is due to what? Due to this heat flow, this you can say. Okay. So, that is why here I have written the energy required to change the temperature of the material is defined by another parameters, that is called specific heat. This specific, due to this specific heat, once heat is flowing over a medium, due to this specific heat the temperature is rising. That means, this heat is converted to, you can say, temperature form. So, in case of a equilibrium condition, whatever the heat is coming, due this heat generally we are converting in temperature. Once we use the convert, or you can say conservation of energy, then what happens, the equation of this heat conduction and you can say this specific heat and heat flux terms can be written as this form. How it is coming, in subsequent slide I will discuss in details. This is the differential form of what is called heat conduction equation, that you can say. This is in transient form. What is this T dot? That T dot is called rate of change of temperature. What is this rho? Rho is called density of the material. Now, this equation, over this equation, if we apply a volumetric types of what is called heat, that unit is let us call Q triple dot and its unit is let us call volumetric heat is heat watt per meter cube, or you can say rate of volumetric heat, that unit will be joule second per meter cube. This you should keep it in mind. Okay. So, let us consider a volumetric heat is applying over this plate. Then this governing equation which I have shown here in differential form is changed to rho c T dot grad K grad T minus Q triple dot equal to 0. This you should keep in. This Q triple dot is coming due to this volumetric heat distribution, or you can say heat distribution per unit volume, this terms is coming. This you should keep it in mind. But in case of point types of heat source, this term is not generally coming. How, that also I will discuss in subsequent slide. Now, to solve this governing equation, whatever the governing equation we get, or you can say whatever the heat conduction equation in tangent form we get. Why it is called tangent form? Because this heat conduction equation, which is a time dependent phenomena, I have considered. Here you can see how this tangent heat conduction equation is coming, that I will discuss in details, because there can be two different types of heat conduction. One is called a steady state, another one is called generally tangent. A steady state which does not depends on time, whereas tangent types of heat conduction is depends on time. That is why I have written here tangent types of heat conduction. To solve this heat conduction equation, there is required some boundary condition and initial condition. What are those boundary condition? Generally, one thing you should keep it in mind, this boundary condition here I have written, generally is in case of heat transfer analysis in welding, we use the boundary conditions which are generally radiation types of boundary condition and convection types of boundary condition. These boundary conditions generally we can define in two form. What are those two form of boundary condition? Little bit I am discussing in detail, two forms of boundary condition. This boundary condition can be one, I am writing here, it can be what is called absolute types of boundary condition. Absolute types of boundary condition means in a body once we prescribe the temperature, directly we are prescribed the temperature, okay. Then generally this is called absolute types of boundary condition. There are generally in two forms we can define this boundary condition. What are those boundary condition? The one form of boundary condition is called absolute boundary condition, and another form of boundary condition is generally called natural boundary condition. Natural boundary condition I am writing in BC. So, one is absolute, another one is natural boundary condition. This you should keep it in mind. Natural boundary condition means here instead of putting temperature, here we used to put generally heat flux. So, here we generally put heat flux. This heat flux generally will be converted into temperature. Okay. Apart from this thing, there is required some other condition that is called initial condition. Initial condition means at time t equal to 0 in case of transient types of heat transfer energy, at time t equal to 0, what is the initial condition of that plate. Generally in this case we used to consider the initial condition of the plate is room temperature, that means ambient temperature. So, initial condition in which condition generally the t equal to 0 the welding plate is subjected to, that condition you need to prescribe, that is called initial condition. Okay. Now, how this radiation boundary condition, convection boundary condition, that things you know very well. Okay. So, that related things I will discuss here a little bit, like radiation boundary condition generally state like they given a body temperature T in Kelvin, the radiation to the surrounding medium at a temperature T0, that means surrounding means ambient temperature T0 in Kelvin follows the Stephan-Boltzmann law. That means radiation whatever the boundary condition we used to use, that is generally developed by Stephan-Boltzmann, that is why it is called Stephan-Boltzmann law. So, due to this Stephan-Boltzmann law, what it states, due to this temperature difference between this plate and what is called surrounding medium temperature T0, there occurs some what is called flux, or you can say power loss. This flux or power loss you can given by this equation. Here you can write this grad I have written here q double dot radiation rad equal to sigma into epsilon t to the power 4 minus t to the T0 to the power 4. What is T? T is the generally you know T is the temperature of the plate and T0 is the ambient temperature, and here sigma generally T is the plate temperature, here you can write plate temperature. Sigma is called its Stephan-Boltzmann constant, here I have already written, this is Stephan-Boltzmann constant. What is the value of this Stephan-Boltzmann constant? You know these things very well, like generally 5.6703, I am writing then also 10 to the power minus 8. Its unit is generally you can easily find out watt per meter square, what is called Kelvin to the power 4, because this temperature unit is this, that is why its unit is k to the power 4 is coming from this equation itself you can see. And here this epsilon is called generally sigma is called generally Stephan-Boltzmann constant. This sigma is equal to 5.6703 into 10 to the power minus 8 watt per meter square Kelvin, and epsilon is called emissivity, which I have already written. In case of steel generally this emissivity value is approximately 0.91, okay. And in case of steel as well as in case of some rust surface, this value is within this range, if you want to put it more accurately, this emissivity value in case of steel you can consider as 0.9134, generally it is varying plus minus 0.068, it is generally unitless, this you should keep it in mind. So, by putting this what is called Stephen Boltzmann constant, what is called emissivity epsilon, you can easily find out how much heat flux loss is taken place or power loss is taken place by radiation, that you can easily find out. So, this radiation, what is the unit radiation heat flux loss, what is the unit of these things, its unit is watt per meter square, that you can easily see from this equation itself. Okay. Now, we will discuss about convection boundary condition. What is convection boundary condition? Here generally this convection boundary condition again can be stated like, given a body temperature T, let us a body which is subjected to heating, its temperature is T, then if the surrounding it is surrounded by a fluid or gas at a temperature T0, then what happens? The heat convection assume that a thermal layer exit with the heat transfer coefficient H convection, here you can see. So, that the temperature difference causes a flux loss, or you can say causes a power loss, which can be given by Q double dot convection equal to H convection, this is called heat coefficient of heat convection, or this is also called film coefficient, okay, or this is also sometimes called heat transfer coefficient, is T minus T0. Always you should keep it, that means heat loss due to convection is directly proportional to temperature difference between the body and you can say surrounding medium, because due to this surrounding medium and the body's temperature, what happens, in between there is create some what is called thermal layer, here I have already written thermal layer. Due to this thermal layer generally there occurs some convection loss, which is or convection heat loss, which is directly proportional to this. Once we equate these things, there generally used to come a constant, that is H con I have already written. This is generally called coefficient of heat convection, or this is also sometimes called heat transfer coefficient for convection, or this is sometimes called film coefficient also. This you should keep it in mind, film coefficient. Equal to T minus T0, 8 convection into T minus T0 is coming. Generally here one thing you should keep it in mind, what is the range of this heat convection value. It generally for steel plate with air, once it's subjected to welding, there we assume its value within a range of around 25 watt per meter square Kelvin. Okay, it depends on how the medium is there. Generally for natural cooling, that it follows this Newton's natural convection law. This was developed by Newton's, that is why it is called Newton's natural cooling of convection, this you can say. And if there is some forced convection, let us see what happens over this plate, there you apply a fan, or there you apply some other medium, there is flowing some water, or there is flowing some air. Due to this thing generally this convection coefficient is varying. So, for this case generally this convection coefficient we can write as this H convection we can write as 0.332, generally you can say conductivity by thickness of the plate. Okay. This T instead of here I am writing this H convection, you can write as H convection equal to 0.332 into K by T into what is called Reynolds number to the power 1 by 3 into Prandtl number to the power 1 by 3. This you should keep. What is Reynolds number and what is T? Here you should keep it in mind, T is called boundary layer thickness, boundary layer thickness, this you should keep it in mind. Okay. And what is K? K is called thermal conductivity, thermal conductivity. This thermal conductivity, what is the unit of this thermal conductivity? This thermal conductivity unit generally is watt per meter Kelvin. I will discuss this thing in details in subsequent details clearly, okay, how it is coming. What is Reynolds number? You know this thing, Reynolds number is rho V d or rho V L by generally mu. What is rho? Rho is the density, V is the velocity, that means velocity of what is called air or water, whatever the medium generally we use, and d is the diameter, or sometime it can be L also, length of the plate also you can say, and this mu is called dynamic viscosity, dynamic viscosity. Okay, this you should keep it in mind. This is also sometimes called dynamic viscosity, and this is also sometimes called absolute viscosity. In SI unit, this unit is generally Pascal second. How it is coming, that also in subsequent I will discuss, because there can be this Reynolds number also you can represent like V d by mu by rho. So, this mu by rho is as term as another viscosity. This is called kinematic viscosity. This you know, you should know these things also, kinematic viscosity. Okay. So, this Reynolds number, and what is Prandtl number? This PR. So, Prandtl number PR generally you can you already very well familiar about this thing, mu Cp by K. What is mu? Mu is called dynamic viscosity or absolute viscosity you can write, and Cp is the what is called specific heat at constant pressure, and K is the thermal conductivity. So, these are all generally dimensionless parameters you can say, right, dimensionless number you can say. Okay. So, how it is that means heat convection, how it depends. So, in a medium you can also calculate the heat convection depending on how the medium is, whether it is stationary or whether it is have subjected to some what is called velocity. So, depending upon these things you can easily find out what is the heat convection coefficient of that medium. Okay. Now, I am going to discuss in details how this Fourier heat conduction equation generally is coming.